So this section deals with the description of light as a ray. And essentially we think of the light as just being a single line, a beam, travelling from the source to the target or the observer or whatever it is that we're interested in looking at or understanding. So for rays, they're represented by vectors which are perpendicular to the wavefront at every point, and a point in the direction of travel of the wave. So here in this diagram, what we have is we have a series of waves. So this is the wavefronts. These are the peaks of the wave, if you like. And they're travelling down in this direction, so that would be the vector which represents the ray. As the wave, or as the ray hits the surface, some of the light will be reflected off, and some of the light will be transmitted through into the transmitting medium. So we have some incident light, we have some transmitted light, and we have some reflected light. And the way that we represent that using rays is just nice and simple. We have an incident ray, a transmitted ray, and a reflected ray. Now these two materials, we have an incident material or medium, and it has a refractive index Ni, and the transmission medium has a refractive index Nt. We'll see what those mean in a little second. So, defining it, we have our angle of incidence, our angle of reflection, and our angle of transmission. And from school level, hopefully, you'll remember that the law of reflection says that the angle of incidence and the angle of reflection are equal. We also have a law of refraction, that Ni, the refractive index in the incident material, times sine of the angle of incidence, theta I, is equal to Nt, the refractive index of the transmitting material, times sine theta t, the angle of the transmitted ray. So this means that n times sine theta is invariant as we go across that boundary. So as the ray travels here into the surface and then gets refracted, then the product of the refractive index and the sine of the angle is invariant. Okay. So that means that if the refractive index goes up, if this refractive index is constant and the angle of incidence is constant, then if the refractive index of the transmitting material is increased, then the angle must go down. Okay. So that's why we get their angle of refraction. One of the more interesting effects that we can have is the light, as it goes from one material to the other. Some of the light will be reflected, some of the light will be transmitted. But if we're going for an internal reflection, so in other words, if we're going from a high refractive index material to a low refractive index, so if the incident material here has a greater refractive index than the transmitting material, then we can get total internal reflection. We'll see a diagram of that in just a second. And so the incident angle here, going from high refractive index to low refractive index, the incident angle is increasing, but the refractive index here, Ni, is constant, and the refractive index up here, Nt, is constant. So Ni times sine of that angle, theta I, will be equal to Nt times sine of theta t. And so if Ni and Nt are constant as that angle changes, theta I, then that angle, theta R, will change as well. So as the angle increases, then we'll see that the refracted ray also increases. And as we go further round, then what we find is that we get to a point eventually where at some critical angle, the transmitted angle, theta t, is 90 degrees. In other words, the light is travelling effectively straight along that surface instead of being transmitted off at some angle. It's then travelling parallel to the surface. And if we go beyond that critical angle, when the angle of incidence is bigger than that critical angle, then what we see is we have no light being transmitted at all here. No light being transmitted. All of the light is being reflected inside the material, and that's what we refer to as total internal reflection. Now that's useful because we can use it in all sorts of different ways in optical systems. The angle at which we start to get total internal reflection is called the critical angle, and if we just say that, okay, well, one of our angles, this theta t, is 90 degrees, then we can see we can work out what the angle, the critical angle is. If theta is 90 degrees, then sine of theta t will go towards 1, and so we end up with a relationship between the critical angle and the two refractive indexes. When we're dealing with lasers, it's quite often the case that if it's a high power laser, we don't necessarily want to move it just in one straight line. We might want to reflect it and bounce it around and move it to where a workpiece is, if we were welding or drilling or something like that. The problem is that if we use just a standard mirror, then we'll see this when we talk about optical properties of materials. Metals tend to absorb light quite strongly. That's why we can't see through them, obviously. And so if you have a high level of instant power, or if it's a pulse system, instant energy, then the metal component can be heated and can actually vaporize and be burned off. So metallic surfaces, metallic mirrors, have a limited range of maximum powers that they can work with. If you want to move around very high power beams, then we can make use of total internal reflection. So if we want to go through a right angle, then using a glass prism at 45 degrees of incidence, that's larger than the critical angle, so all of the light is reflected internally, and we get the beam being deflected through that right angle. Obviously, at these points where it hits the front surface and the bottom surface, then you will also get a little bit of reflection going back the way. So you will get some loss of light, but that will not be to the detriment of the material. The material won't be damaged by that in the way that a metallic surface would be. We can use a total internal reflection to get the laser beam directed to where we want it to be. We can also use it for making the systems in an optical system much more compact. So for example, oops, sorry, let me just raise that. What's shown here is with the right angle prism again, but we have it at 45 degrees to the vertical, so the light comes in, gets bounced off the two surfaces and comes back in the same direction again. It's displaced obviously by some distance, What use is that? Well, if, for example, you have a telescope, then it might be that you need a big distance, a large distance between these two lenses. And one of the ways that we can make that shorter is if we have two prisms. I'm going to draw this really badly, so hopefully you can get some idea as to what I'm trying to do. The light comes in, bounces around, and goes out. Oops. Out through. So in this case what we've got is we have a telescope, and in this case what we have is a monoscope. So if you imagine that being mirrored, then you would have a pair of binoculars, and these little prisms allow you to compact and squash your optical system of a certain length into a much smaller space. So it can be useful for things like that in terms of design. Another aspect of the light as it gets reflected is the effect that it has on its polarization. In the diagram down here, the way that I've drawn this is that we have a ray coming in at some angle theta I, and we have some light which is polarized at some arbitrary direction. Remember, we can break that down into an x component and a y component for whatever angle of polarization that we have, and I've represented that by that line being the in-plane polarization, the y, if depending on how you've got your axis sorted, and the dots being the out of plane, the perpendicular to the plane polarization. So those two polarizations represent our x and our y, and so we can represent any angle of polarization that we care to consider. When the light comes down and hits the surface, again what we've got, some of the light will be reflected, some of the light will be transmitted, and what we want to know is we want to know how much light will be reflected and how much light will be transmitted. Well, it turns out that it depends very much on the polarization, and again when we come on the next section looking at optical properties of materials, we'll do this in more detail, but for the moment let's just consider that if we have both polarizations going in, if we pick the right angle, the correct angle, and by the correct angle I mean Brewster's angle, then only one polarization will be reflected. And you can see that that's the one which is perpendicular to the plane. So in the transmitted beam we will have both polarizations, in plane and perpendicular, but in the reflected beam we only have perpendicular polarization. Okay, that's great. You say, what good is that? Well, one of the things that we might want to do is to control the polarization and use the polarization, because lots of things depend on the polarization of the light and how it interacts with them. So polarization is just another way, another thing which we can control. And if, for example, if we want to use light to take measurements, then if we measure the polarization before some interaction and after some interaction, then that gives us information about what actually happened in that interaction. So Brewster's angle is this angle whereby the only one polarization is reflected, and it's given by that relationship there, that the incident angle is Brewster's angle and the transmitted angle is 90 degrees minus Brewster's angle. So Ni sine theta b is equal to N2 cos theta b. Why is it cos theta b? Because we've got 90 degrees minus, so that's N2, sorry, N2 sine of 90 degrees minus theta b. Yeah? So Brewster's law, or Brewster's angle, can be written as the tan of Brewster's angle is again related to the ratio of the two refractive indexes, in the same way that we had for the critical angle, only there it was a sine of the angle. As I say, generating polarized light is something which can be useful for various applications, and often in lasers what we're interested in is having as much information about the light as we can. So we want to know its frequency and its direction and its coherence and so on, but also we want to know about its polarization usually. So the little model I've got down here, the little diagram, is a helium neon laser. So this is a small gas laser. So what we have is we have a tube, like a neon tube, and it's sealed at both ends with mirrors. And this tube is filled with some helium and a small partial pressure of neon, and we apply a current through the gas. So we apply a large voltage across it, and that will then cause a current to flow through the gas. The electrons that are passing through the gas will bump into the atoms and give them some energy, and then as those atoms relax, they'll give out some light, and that's how the neon lights work. But we can go one better. We can make that a laser. And we make it a laser by putting some feedback into the system by using these mirrors. So the very simplest way of thinking of a laser is a positive feedback loop. So what we're doing is we're passing current through this gas, and it's exchanging energy, it's depositing energy into the atoms of the gas, and the gas is then relaxing, it's getting rid of this excess energy by giving out light. And when we think about lasers, the word laser, light amplification by the stimulated emission of radiation, it's an acronym, light amplification by the stimulated emission of radiation. What happens is that the light starts a chain reaction of creating more light. Okay, so we might start off with one little piece of light, a photon, a particle, or whatever, and then we end up with 2, and then 4, and then 8, and so on. And so the signal grows exponentially as it travels backwards and forwards through these, between these two mirrors. This mirror here will be maybe 100% reflecting, and this mirror will be, let's say, 98% reflecting. So 2% of the light will actually be allowed to come out. Okay. So that's the system as described. And what we're interested in here is the fact that inside the laser, the light which is being generated will have a random polarization. So it may be polarized in one plane or another plane or something in between. And so again, what we represent that by showing both polarizations, perpendicular and parallel to the plane here. Now, as it hits the Brewster's window, as it's called, this piece of glass, which is just at Brewster's angle, then only the perpendicular light will be reflected at that point. And basically what's happening is that perpendicular light is going out through the side and being lost. Whereas the light which is travelling straight through, the light which is transmitted, will have both polarizations, but as a positive feedback loop, we've got lots of gain for the parallel polarization, but we've got lots of loss for the perpendicular polarization. So most of the light will therefore find its way into the parallel polarization. Okay. Positive feedback loop. Anything which has a small advantage, if you've got two different signals in the same positive feedback loop, if one has just a tiny little bit more gain than the other, then all of the energy is going to go into that stronger signal. Okay, and that's what happens here. So the output from the laser will be plane polarized, and it will be polarized parallel to the plane, the plane of this diagram here. Typically the ratio might be 100 to 1 in terms of the amount of light which is polarized parallel to the amount of light which is polarized perpendicular to the plane. But you can do better than that by using other optics. Okay.